hear me? Yeah. Can you hear me?
Yes, sir.
Okay, good. So last time what we saw was an FPT algorithm for the following problem. So the question is, does G have a vertex cover of size most k, and parameter is not k but k minus the LP opt of G. That is, you take the LP corresponding to the graph, vertex cover LP, and take the optimum value, and k minus LP opt is the parameter. And what we saw was so I'm going to use this term O star, which means that I'm ignoring some poly in Mn term. In this case, it's more like Mn root n or something, because M root n is to solve the LP and you're trying to do it n times. Okay, so this is what we spent most of the time last time, and the idea was to first get to all halves solution for the LP, which we said we can do by solving the LP, removing a vertex at a time and looking for how the drop in the LP value is. And once you reach all half solution, we said just pick any vertex and branch, either include it in the solution or include all its neighbors into the solution. We argued that this k minus LP in each of the branches drops by at least half. Okay, so it's like, so the height of this is 2 times k minus LP opt, because the drop is only half, and it's a two-way branching, so it's 4 power k minus LP opt. And we saw some corollaries, and we will see more today. 4 power k minus maximum or any matching, in particular maximum matching. So to test whether there is a vertex cover of size at most k, you have an algorithm whose running time is exponential in k minus the size of the matching. Okay, and using this as a corollary, we saw that the odd cycle transversal problem has O star 4 power k algorithm. So the O star notation is clear, right? Because it's basically, our focus largely has been on the f of k term. So by O star, I mean 4 power k times some poly in n, okay, or plus some poly in n, doesn't matter, both are equivalent. And what is the OCT problem? Your input is, parameter is k, and the question is, does there exist subset S contained in B right? So, can I remove some k vertices to get the graph bipartite? And we gave a 4 power k algorithm by a simple reduction from OCT to this vertex cover above matching. Okay, let's just go through that quickly, and I don't know how many people tried proving that little exercise I had. So the proof is by reduction to vertex cover above matching. Okay, so this problem. So what is the reduction? So here is my graph where I want to know whether there are k vertices whose removal makes it bipartite. So this is a OCT instance, and we're going to reduce it to my G prime contains 2 copies of G, and I add the edges between the corresponding copies of the 2 copies of these vertices, right? So you have, so let's call this my vertices are V1, V2 up to Vn, or V11 and V12, V22. Okay, so there are n vertices in my original graph. I just take 2 copies of them. So here I have the entire graph is here, and I'm drawing matching between the corresponding vertices, right? So a copy of that vertex has an edge to copy of the other vertex, and no other edges are there between. And what is the claim? So let's call this as G prime. G has an odd cycle transversal of size at most k, if and only if G prime has a vertex cover of size at most size of B plus k, right? So this is now if you look at G prime, any vertex cover has size at least the size of this matching, which is the size of B. So I'm allowing some k more vertices, and this happens if and only if there is an odd cycle transversal. So that's a claim. Okay, so let's see how. Anyone tried the proof? You did? Okay, it's all fairly easy, right? So if you have an OCT of size k, then so let's just look at this. G, which means that there are some k vertices. If you remove it, the graph becomes bipartite, right? So this is the situation because this is the same copy. So I have k vertices. If you remove these k vertices, the graph becomes 2 independent sets, right? So there is a matching. Now I have to produce you a vertex cover which picks exactly one vertex from each of the matching edges and 2 vertices from each of these k edges. So up to k edges, it can pick 2 vertices from the matching edges, and for other matching edges, it should pick 1. Okay. So the natural thing is for these k edges, I am going to pick both and for these you pick for one of them pick one side and pick one of them the other side, and that the size of this set you have picked is at most cardinality of V plus k, because you picked one from each of the vertices of the original graph plus some k more because you have picked 2 vertices from this. And why is it a vertex cover? you argue that the complement is an independent set, right. So, I pick the complement contains this and this, right, but these two are independent sets to start with, and there are no edges between them by construction. So, that is it, right. So, in one direction, if you have an OCT of size at most k, there is a vertex cover of size at most b plus k, and conversely, if you have a vertex cover of size at most size of v plus k, that means at most k of these edges you pick both endpoints. So, find those edges and that correspond to a set of vertices. I claim that if you delete those k vertices, what you have is a bipartite graph, and you just basically reverse the argument. Okay. So, now to complete the picture, to give an FPT algorithm for OCT, what we need to do is to check whether my G prime has a vertex cover of size at most n or v size of v plus k, and I use this algorithm, corollary 1 algorithm, which this is the solution size. In our case, it's cardinality of v plus k minus the matching size, which in our case cardinality of v. So, overall you get a 4 power k algorithm to determine. So, to get check if G prime has a VC of size. Okay, so that results in O star. So, next week or the week after, we will see a better algorithm for OCT, a 3 power k algorithm using a completely different technique. Okay. So, let us see more applications of this. Okay. So, it started off as an interesting parameterization where you just say solution size is not the parameter, but something else, some difference between solution size and some guarantee. But it just surprisingly gave this for standard parameterization of OCT, it gave me an FPT algorithm through this reduction. Okay. So, let us look at some SAT version. Turns out that also has some interesting relation to this vertex cover above matching. So, let us look at, so we saw this max SAT version. But the standard parameterization of max SAT is, our input is some CNF formula, and your parameter is k, and the question is, is there a satisfying assignment? Is there an assignment satisfying at least k clauses? Right? This was the standard version of SAT, max SAT, and we saw very nice kernel with at most 2 k clauses and k variables. One can do some branching algorithm and get an FPT algorithm for this, right. Once you have a nice kernel, you can do get a good FPT algorithm. Now, I can formulate the problem slightly differently as follows. So, we will parameterize from the other end n variables, m clauses. Now, I ask, is there an assignment that satisfies at least m minus k clauses? You want to satisfy, so this is sometimes called almost SAT. So this is also a version of maxsat. I want to maximize the number of clauses, but my parameter is changing. Earlier my parameter was the number of clauses I could satisfy. Now my parameter is number of clauses you are falsifying. Right? You want to satisfy everything except at most k clauses. Right? So now my parameter is it's a sort of a minimization problem. I want to minimize k, and I want to satisfy everything except k clauses. My parameter is now k. Okay. So is this, first of all, can this be fixed parameter tractable? Okay, I never asked this question before for any other problem. So the reason I am asking means the answer should be obvious, right? Can this be fixed parameter tractable? So what does this mean? Is it possible to have an algorithm whose running time is f of k times some poly in Mn? Exactly, right? So if I manage to get such an algorithm, which means that there is some f of k, in fact, let's write this as plus poly in Mn kind of an algorithm. When k is 0, what is this question? Is the formula satisfiable? Right? I am asking, can you satisfy this formula? Is there an assignment that satisfies all clauses? So when I put k equal to 0, I have a polytime algorithm to answer that question, which I don't expect, because it's an NP complete problem. So you don't expect an FPT algorithm for this. Okay. I mean, a similar, if you want an analogous example, would be, let's take graph coloring. Okay. And I ask, is the chromatic number equal to k, or less than or equal to k, where k is my parameter? Okay. Can that have an FPT algorithm? The same kind of an answer, right? Why? Tell me why. So k is 0 or 1, it's polynomial time. We know that. Testing whether chromatic number is 0 or 1 is polynomial time. So it doesn't contradict it. 3, right? For some, testing whether chromatic number is 3 is a graph 3 colorable is an NP complete problem, right? So whenever for constant k, the problem, for some constant k, if the problem happens to be NP complete, you don't expect an FPT algorithm. So even for constant k, the problem is NP complete, then with that parameterization, you don't expect an FPT algorithm. Okay. So that's, so for example, for 3 coloring, just 3 alone is NP complete. So you don't expect an FPT algorithm for this, right? Similarly here, this would imply a polytime algorithm for SAT, which is unlikely, right? But the question still makes sense if I say it's a 2CNF formula, right? Because we know that 2 CNF SAT is polytime solvable anyway. So, there is no contradiction yet. Okay. So, let me call this almost 2 SAT, and now let us ask this question. Then we do not know, at least this argument does not hold, because we know if you have 2 CNF formula, you can test in polynomial time whether it is satisfiable or not. So, it is still possible that you can, this could be in FPT, right. Polytime algorithm for SAT, which is unlikely unless F is a 2 CNF formula. No, I won't say unless F is something special. F is some formula where polytime algorithm for SAT exists. So, now let us look at this question. This is my question now, which is given a 2 CNF formula where every clause has exactly 2 literals, let us say exactly, right. Sometimes the definition allows you at most this. Interestingly, it turns out to be equivalent to vertex cover above matching. Okay. What does it mean by equivalent? I mean there is a parameter preserving reduction between both problems. Okay. So, like we had a reduction from OCT to this above guarantee, above matching vertex cover, one can, so this is my problem. So, let us just go back one more time. So, I asked if it is not 2 CNF, is it even fixed parameter tractable, and we argued it cannot. Note that not just fixed parameter tractable, I cannot even have such an algorithm, right. Fixed parameter tractable means it is f of k times some poly in Mn, and I argued that that is not possible for if it is a general SAT. Even worse, you cannot even get such an algorithm for that problem, because the same argument, because when I plug in k equal to constant, this becomes a polynomial, which we do not expect even for k equal to 0. Okay. But here, can we at least get an m choose k kind of an algorithm? So, what is, okay, another way to phrase this is falsifying at most k clauses. Can you give me a, I mean, we want to design an FPT algorithm, and the way I am going to do it is to show that this is same as vertex cover above matching problem by giving you some equivalence. But before that, can you at least give me some m power f of k times poly in n kind of an algorithm? Try all, I mean, we saw this for vertex cover. I want to know, is there a vertex cover of size at most k? I try all possible subsets of size k, delete it, check whether the remaining graph is edgeless, right? That is like an n choose k algorithm. My question is, can you tell me something like that kind of an algorithm, some m choose k kind of an algorithm? So, you guess, you guess the k clauses which you want to falsify. So, go to their clauses set every literal to be false because we want to falsify that and simplify the remaining formula. Go to the remaining formula. Now I ask, is it satisfiable? Since it's a 2-sat formula, you can check that in polynomial time, right? And if it's not, you make another guess and run through all possible guesses, and you get something like an m choose k times poly in the input size, right? Is that clear? So, guess the k clauses we want to falsify, check whether the remaining formula is satisfiable. So, this is good. At least I said if it's not 2 CNF, then you can't even get such an algorithm because that would immediately imply a polytime algorithm for SAT. Okay, so now I want to just, so imagine how is this, yeah, okay. I'll give you equivalence between this problem and the above matching vertex cover. One, okay, so there is a parameterized reduction. So, such an algorithm, okay, I might as well use, we started using, we have been using the word FPT to say a problem is fixed parameter tractable. It also stands for the class of problems, parameterized problems solvable in fixed parameter tractable time, right? Like P stands for all polynomial time solvable problems. FPT stands for the class of parameterized problems which are fixed parameter tractable, and this is called XP, is a class of problems for which you have such an algorithm, okay, where f of k is at the exponent. So, this says that this problem, so FPT is contained in XP because this is even stronger notion than this what you are demanding here. And I'm using a word parameterized reduction. All this will come in handy later. Vertex cover above matching. Okay. So, what is this problem? This is the, we want to know, is there a vertex cover of size at most k, and the parameter is k minus, you are given a maximum matching. So, this is this problem is what I call vertex cover above matching, and I want to show that there is a reduction from here to this almost 2-sat problem. Okay. Ideally, we would like the other way reduction to get an FPT algorithm for this problem, right? Here is a new problem. I want to design an FPT algorithm. Like OCT, if I can take this and reduce to vertex cover above matching, I can use that algorithm to solve it, but I will give that reduction as well. But this reduction is fairly easy to see. We will see this first. This shows that actually, this problem is more or less the same as this problem. And by parameterized reduction, what I mean is that the parameter should go okay, I'll get to that later. Okay. So, you are given an instance of this problem where you are given a graph, right, and you are given a matching. Okay, there are different ways of phrasing this. One way to state is this. Okay, I ask, is there a vertex cover of size k plus the size of the matching, because this is a lower bound on the vertex cover anyway. I am giving you k more, and now my parameter is k. Okay, this is the same, because earlier I just did k and put k minus here as the parameter. So let's look at this version of this problem, where I am interested in. So you are given a graph G and a maximum matching in the graph, and you know that any vertex cover must pick at least one from each of these edges. Now I am saying, okay, on up to k edges you are allowed to pick both endpoints. Okay, is there such a vertex cover is the question. All right. Now I want to formulate it as a two-sat problem and ask this question: can you satisfy all the clauses except k? Okay. So it's going to follow more or less the linear programming formulation of vertex cover, because it's two variables per class. But two variables in the inequality will correspond to a two-sat instance, right? So what am I going to have? From here, I am going to construct a formula f. This formula is looking like this. It's a 2CNF formula. For every edge in the graph, I am going to say xi or xj, right? This is the vertex cover. So there is a variable for every vertex. That's all the variable is. For every edge in the graph, I am going to say either pick xi or xj. One of them must be in my vertex cover. Now let me also insist, for every edge in the matching, pick exactly one. I am going to add some constraints saying that. Okay. So how do I add that as a two-sat thing? Right. So I am going to say, for every uv in the matching given to me, this constraint already tells me that one of it is picked. Now I am going to say that don't pick both. How can I say that? Xi intersection, I have to write an R, but I want to write an R, right? Because 2CNF means it's ANDs of R. How do I say don't pick both? In one edge, I am talking about one edge. The AND will take care for every edge. In one edge, I am just saying both should not be in. That's it. XU bar or XB bar, which means that one of them is out. That's all it is, right? One of them is definitely out. You might throw away both of them out, but no, because this constraint will make sure that you will pick one of them, because everything in M is also here. So for every edge, pick at least one, and for every edge in the matching, don't pick at least one. Okay. Now I have added a two-sat formula. Let's understand what happens to this k, or what is this property of this, right? Now what is obvious is that, I mean, the way I have actually written down is that if, okay, so G has a vertex cover of size if and only if, that means if I have a vertex cover here which picks exactly one vertex from each of the matching edges, you need at least one, suppose it picks exactly one, then this formula would be satisfied, right, because you take that vertex cover, set for all elements vertices in the vertex cover, set them to 1, for everybody else set it to 0. Since it is a vertex cover, this will be satisfied. Since it picks exactly 1 from each matching edge, this will be satisfied. So, f will be satisfied. Okay. You can generalize this a little bit and say G has a vertex cover of size at most plus k, which means up to k edges it is picking both endpoints. Then I will violate those k clauses, because if you pick both endpoints, if and only if at least all but at most k clauses are satisfied. So, here is my claim. Let's try and prove this, right. So, you are in the input here, you are given a graph and maximum matching. From this, I construct this formula which says that for every edge at least one endpoint is there, for every edge in the matching at most one endpoint is there. Okay, that is my formula. My claim is G has a vertex cover of size at most the size of the matching plus k if and only if there is some assignment to the formula, there is some assignment to the variables of the formula which will satisfy all but at most k of these clauses. Okay, let us just verify this slowly. One direction is easy, we already saw, but the other direction requires a bit of work. So, one direction, you take the vertex cover given to you, right, and since its size is at most this plus k, in at most k of the edges of the matching it picks 2 endpoints, right. Go and remove those k clauses from here, because you are stuck, you are picking both endpoints. So, you are not going to satisfy those 2 clauses, those k clauses, just remove them, then that assignment would satisfy everything except the k clauses, because it is a vertex cover. So, it will satisfy all of them, and except for those k edges it is picking at most one, exactly one from the other matching edges, it will satisfy this. Okay. The other direction, if you have an assignment to this formula which satisfies everything except at most k clauses, the problem is if it falsifies some of these clauses, then what do you do, right. If it falsifies all the k clauses here are falsified here, then good, those k matching edges I pick 2 and otherwise 1, I am done, I will get that plus k. If it falsifies that some of these clauses, what I can do is I can create another assignment which will still satisfy at least that many clauses, but it will not falsify any of these clauses. Why? So, suppose I have an assignment that falsifies one of these clauses, let us say some x1 or x3, right. There was this edge 1 3, it falsified it. Now, I am going to change it and say okay, I am going to set x1 to 1. I will gain that clause. What do I lose? I may lose a clause here which contains x1, but this is a matching. So, at most one clause will have x1 here. So, I will gain this and lose at most 1. I may not even lose anything, because if x1 is not even here, if it's not even part of the matching, then I won't even lose it. But even if I lose, I'll gain at least one, because by setting x1 equal to 1, I may even have more clauses satisfied here. So I'll gain at least one and lose at most one. So I am actually doing better. So I have a formula which satisfies all but at most, sorry, I have an assignment that satisfies all but at most k clauses of this formula. I can get another assignment that satisfies all but at most k clauses, and it will satisfy all these clauses. Then from that, I know it is falsifying at most k of these clauses. That corresponds to k matching edges there. Pick both endpoints of those edges, and you have a vertex cover of size at most this much. Okay. So what we have shown is that if I have an FPT algorithm for this almost 2-sat problem, where the parameter is this k, then I have an FPT algorithm for this matching, vertex cover above matching. But we are in an opposite situation where we know an FPT algorithm for this and we are trying to design this. So I'll give you an opposite reduction that will show that these two problems are equivalent. Okay. It's also interesting because the SAT looks like something on formula logic, but it turns out this is equivalent to some graph problem. Okay. So we want to give the other way direction, right? Right. So by parameterized reduction, what I mean is that this parameter here is preserved. Somehow the k might become some f of k, but it does not get mixed with the input size or anything like that. Okay. So I'll give you an example which is not a parameterized reduction, so you understand, because that's another thing which will be useful when we talk about the notion of hardness later. So an example which is not a parameterized reduction, some experts here. Click to independent set. No, that k goes to k, right? Vertex cover and independent set. So you look at this vertex cover problem where you want to find a k sized vertex cover, and let's look at an independent set where one is interested in k sized independent set. There is a reduction from vertex cover to independent set, right? Because basically the set complement of vertex cover is independent set, right, in the same graph. So you can reduce from gk to gn minus k. G has a vertex cover of size k if and only if it has an independent set of size n minus k. That's not a parameter preserving reduction because k goes to, k's purity is not preserved. You mix it with the input size n and so on. So that's not a parameter preserving reduction. Whereas here this k goes to k. So it's a parameterized reduction. K need not necessarily go even to k, but some function of k is fine. Okay, so now I want to give a converse reduction from so there exists here k will go to k. So then I can use my 4 power k algorithm here, FPT algorithm, to get a 4 power k FPT algorithm for almost 2 set. Okay, so the reduction, so what is given to me is a SAT formula F, right. So, I have an F which is and variables it is a 2 SAT formula, and I want to get to a graph such that whatever is not satisfied corresponds to those edges from which I pick 2 endpoints in the vertex curve. Right. So, my graph will have the following structure. So, x1 bar, x2 bar, oh, there is also a k, and I will draw an edge. And then every formula Fi is also some so F1 would be some 2 literals it will have, F2 will have some 2 literals. So, L11, L12, L22. So, this is my raw structure for variables and clauses. In fact, I am going to do more. And then there is a natural connection between the clauses and the variables. So, for example, if F1 happens to be, let us say, x3 or x5 bar, say, then I will have my x3 joined to L1 and x5 bar will be joining to this. Okay, so this is my whole graph. Okay, the graph clear? Maybe we will do an example. Actually, I will, for the converse, I need a little bit more, but let me start with this. So, let us say my formula suppose is x1 or x3 and x2 bar. So, this is my formula. My graph will look like okay, so this corresponds to F1, this corresponds to F2, and F1 is x1 or x3, so it will be x1 or x3. And the second clause is x2 bar or x3, so it will be an x4 or x2 bar. That is my graph. Okay. So, what is the number of vertices in the graph and or what is the matching size? it is a perfect matching. So, number of vertices here is 2m plus 2n, right, exactly. So, the matching size is m plus n, right. There is a matching, m corresponds to the number of clauses, n corresponds to the number of variables. Right. So, we will do more. Okay. So, now my claim is exactly what I want. There exists an assignment falsifying at most k clauses, implies there exists a vertex cover of size at most m plus n plus k. Okay. So, it is one direction I am saying, the opposite direction requires some more gadgets to my construction yet. So, what this is not the complete construction, but I think it works for one direction. So, let us try and show this, right. So, if you have some assignment that satisfies, that falsifies at most k clauses, so I take that assignment, right. Which means that it will set, if x1 is set to 1, I am going to pick this into my solution, I am going to construct a vertex cover, right. And if x1 is false, I am going to pick this into the vertex cover. So, clearly I would have picked a vertex, I picked n vertices for each one of them, and for anything which you have falsified, I will pick both endpoints. Okay. So, I will have n plus 2k, right. Now, for the remaining m minus k, I claim that I will be able to pick exactly 1 to cover that, right. So, what do I know about the remaining clause? I know that this assignment satisfies that clause, right. So, I know that in this corresponds to a literal, this corresponds to a literal, one of this is set to true. So, I have picked the corresponding literal into my solution in the vertex cover already, whatever as I have picked. So, you pick the other endpoint, right. Suppose this corresponds to this literal and I have already picked it into my solution, or in other words, that literal satisfies that clause. That means this would have been picked in the vertex cover. That means all these edges, in particular this edge, would have been covered by that vertex. So, I do not need to pick that vertex, I will pick the other vertex into my solution. Okay. So, I claim that I just need one of each of the other clauses. So, totally I will have a vertex cover of size n plus m plus k. I picked n plus m plus k vertices, and why is it a vertex cover? It covers all these edges, it covers all the cross edges, plus it also, the key thing is to cover the across edges. That I argue by saying that each of the remaining clauses is satisfied by my assignment. So, there is a literal which satisfies it. So, the corresponding vertex on the other side must have been already picked into the solution. So, you are free to pick the other vertex. Maybe both are picked into the solution, then you just pick arbitrarily one of them. Okay. So, just one for each of the remaining clauses is enough to get vertex cover of this size, right. So, that is one direction. To show the other direction, we want to show that if there is a vertex cover of size at most, it is very similar to the earlier argument. If you have a vertex cover of size at most n plus m plus k, then at most k of the matching edges have 2 vertices picked into the solution. It will be nice if those k edges are here, then I can get rid of them and I convert back to a vertex, an assignment that satisfies at most k clauses. But if my k of those are picked, let us say it picks both of this, then that is sort of an ugly thing to deal with. So, what we will do is we will make k plus 1 copies of these edges. So, my construction is not just x1 bar, I will have k plus 1 or k plus 2 copies of this. Everything k is given to me in advance, right. So, I will take some k plus 2 copies and we will draw these edges for these guys alone. And when I draw these edges, all of them, so if f2 happens to correspond to x2 bar, then all x2 bars will get attached to this vertex. And if this corresponds to some other thing, all of those guys will get attached to that. So, that is my construction. Okay. The forward direction still will go through. I mean, it is still polynomial time, everything is fine. The forward direction will still go through, because if you have an assignment that falsifies at most k clauses, pick, remove those, pick both endpoints of those, and then pick corresponding xi's here, and then you are free to pick exactly one from each of the remaining formula. Now, for the backward direction, if you have a vertex cover, so it is not n plus m anymore. What is it now? The number of matching size and the number of vertices would be m plus k plus 2 times n, right. So, that is all it is. And so, now you will be looking for a vertex cover of size now you have k edges have both endpoints picked, it will be these edges, because it is not possible, there is no reason to pick some k of this here where you pick both endpoints, but in these two you have picked only one, their adjacencies across fi's are exactly the same, right. So, there is no reason you will pick both endpoints of any of these edges. So, both endpoints are picked from the clause edges, and then the reverse direction goes through. Okay. So, net particularly from claim 2, there exists an O star 4 power k algorithm. Not just that, these these two problems are equivalent. So, that means any improvement you have on this would carry over to an improvement for that problem. Okay, so this k minus LP parameterization it started off as an interesting parameterization, but it actually has a lot of nice reductions, and so implications for FPT algorithms for a number of other problems. Okay, with this I think I will conclude bounded search trees. The big idea, we did not do bounded search, we are doing reductions today, but the big idea of bounded search tree is somehow we want to identify some small substructure, some small number of elements, which one of which you can force, that gives you a handle to branch. Okay. So, maybe I will give one more example from branching algorithm for the standard max sat. Right. Yeah. Okay, branching bounded search trees, they're all, we keep standard parameterization of MaxSat. So you're given a CNF formula F, parameter is K. Does there exist an assignment satisfying at least K clauses? Okay, we know we have we have seen 2K clauses and K variable kernel. What that means is, given an arbitrary formula, CNF formula like this, in polynomial time, we can produce an equivalent instance which has at most 2K clauses and at most K variables. Okay. That apart, either you may want to kernelize it, let's even say I may not want to kernelize it. Now, I want to just think in terms of branching algorithm to answer this question. How would we go about doing this? We have to make a choice somehow, right? Branching means some choice. More importantly, in each of the branches, the measure should drop. Then we have a good handle. And the measure for us is the number of clauses satisfied by your assignment. So, how would you branch? So, you given some CNF formula, I want to satisfy at least K clauses. Take one clause, okay.
Branch with all.
Okay, so let's say I have a clause which is x1 or x7 bar or x3 bar or x4. This is one such clause. So, what are you going to do? We don't know that, right? Or it is not satisfied. Okay. So, okay. So, what you are saying, there are 5 branches. Either it is satisfied by x1 or it is satisfied by x7 bar, or it is satisfied by x3 bar, or it is satisfied by x4, or it is not satisfied at all. What happens to K in each of the branches? In last branch, K does not change, which is the bad news for us, right? We want K to drop everywhere. Remember, in the above LP thing, we worked hard to make sure that there is a half drop here and half drop here that gave us this thing. So, in the last branch, in all these branches, K drops by 1 because you have satisfied this clause. Now, you ask, okay, in the remaining formula, can you satisfy him? But in the last branch, K does not. So, this may not be there. And remember, in like feedback vertex set, it was always useful to do some pre-processing before branching. That helped. Okay, it crucially helped when we said the top 3K vertices, one of them must be there. That was only if the minimum degree is at least 3. So, we needed some pre-processing. But of course, when you think of a branching, you will see whether some pre-processing is useful or not. So, what other kind of branching we want to do? So, one is we picked a clause and we are trying to branch. What can you do otherwise? pick a variable and branch. Okay. So what happens? So I pick some variable and branch. Let's say I pick x1, set it to 0 or set it to 1, and what happens to k?
If1, that place we have to where x1 is there, those we don't need to.
That, so k will drop by that much.
Here where x1 bar is there, will drop by that.
Right. So will we
in any branch neither x1 nor x1 bar. There is no x1, there is no x1 bar.
There is no x1, no x1 bar, you don't have to worry about. You pick a variable that appears clearly, right? But so that's not a problem. But in suppose you have a variable which appears only positively and doesn't appear negatively in the other branch, you have
no x1 bar.
Right. Don't use that branch safely. If a variable appears in one way, right? Suppose you have a variable that appears only negatively in the entire formula, what stops you from just setting it to 0? No problem. It's not going to conflict with anybody else. Just set it to 0, satisfy all, you get it for free. No branching at all, right? So your pre-processing rule. What is the pre-processing rule? If any variable appears only in one form, either pure form or in negated form, set it and packet all the clauses you satisfy in that process. K drops by that many with no branching. Okay, so keep doing this pre-processing. So pre-processing, pick, okay, set all variables that appear in only one form, that is pure or negated, set the variable appropriately. See, you wouldn't think of this pre-processing right away. You went to the branching and then you realize that, in that branching, if this happens, then, but actually that's a good news, even though k doesn't drop. So you just go ahead and do this pre-processing, and after that, so now branch on variables, right? Pick any variable that appears, in one branch I'm going to set x equal to 1, in the other branch I set x equal to 0. I'm trying both choices, and my k would drop by number of clauses with x, and similarly here it's since we have ensured that both of them appear at least once, k would drop by at least 1 in each of this, and you will have a 2 power k kind of a branching algorithm. Okay, here is another version of this is probably already in the assignment, but that's okay. Does there exist a satisfying assignment with at most k ones? Right? This is called min one sat. Okay, actually 2 set. Let's even say. So now I have a CNF formula, 2 CNF formula. And what am I interested in? I want a satisfying assignment. It has to satisfy every clause, but you are allowed to pick at most set or at most k of them 1. Okay. First of all, is the problem really NP complete? Can you formulate vertex cover as min ones 2 set? That's it, right? You draw the standard thing which you have seen again and again. For every edge ij, you draw xi or xj. Look at that 2 set formula. Looking for a k sized vertex cover corresponds to looking for a satisfying assignment for this with at most k of the variables set to 1. Clearly, this has a satisfying assignment because it's a monotone formula, it's all pure. So, I set everybody to 1, it will satisfy it. But I want a satisfying assignment with at most k ones. So, it's a generalization of vertex cover. Why is it a generalization? Because I might have pure and negated literals in each of the clauses, whereas for vertex cover formulation, it's a monotone formula. Okay, so now let's think about how do I come up with a branching out. So now here notice that for every clause I want to satisfy it, because the earlier formulation I want to satisfy at least k clauses, not necessarily all of them. But here I want to satisfy every clause, so that gives you a handle to branch, right? So what do I start with? Pick a clause. No, if the clause is then you have to either you set x3 to 0 or x2 to 0 to satisfy this. But what happens to k? K doesn't change, because k is measuring the number of ones, right? You set somebody to 0, tough luck, right? That k doesn't drop. So, okay, so pick a clause which is of this type, which may or may not exist. Sorry, what? No, which clause are you talking about? The previous thing, okay. Hmm. Hmm. No, x3 is set to 0. What do you, when you say you're setting x3 to 0? You might say I will set x3 to 0, then I might set x2 to 1, but that may or may not be the right choice because it's going to affect some other thing. So, you really want to do something which is sort of forced. Right. So, if you are lucky, if you are managed to get such a clause, pure clause, then you can branch by setting x3 equal to 1 or x2 equal to 1 and k drops, because you made one guy 1. So, number of ones. Now, you look for in the recursive sub formula, is there a satisfying assignment with at most k minus 1 ones, and k minus 1, that is good shape. But what if you do not have such a clause? Hmm. Hmm.
We said both x2 and x3 is 0.
Mm-hmm.
Because that won't affect, we need at most k ones.
Right, but k doesn't drop, right? Remember,
K doesn't
it doesn't affect.
So those clauses not required, just it is not affecting working on the formula.
No, because there may be somewhere else it will be like this. If you set this to 0, you have a problem. If you set both to 0. Okay, so looking at this for a class, you can only say that to satisfy this, I have to put x3 equal to 0 or x2 equal to 0. There is no other way I can satisfy this. So it gives me a way to do some setting, but it doesn't help me because k does not drop. So remove what clauses? Double or even single negation also is a problem. Even this is a problem. Because what do? I do x2 equal to 1 or x3 equal to 0, but here k doesn't drop. Yeah.
So if a variable is occurring in negation every time it occurs, then we can reduce the number of clauses to be satisfied.
Okay, you are close. So can you say it again?
If a variable is occurring in negation every time it occurs in a clause.
Oh, okay, okay. If a variable appears only negated in all its occurrences, sure, you can just set it to 0 and get rid of it. Yes, I agree. But it may not be like that. It may have some negation here, some positive here. Yes.
Like for pre-processing, I'm saying we can reduce the problem size if that happens.
Yes, I agree. That's a pre-processing. If a variable appears only in negated form, great. Set it to 0 and reduce the formula, and you don't bother. K doesn't change. No problem anywhere. Yeah. So we can write that. So if a variable appears only negatively, set it to 0 and remove all satisfied clauses. But that's not the problem. Our problem is that there are variables that are appearing both positively and negatively. I do not have a pure clause. Okay, does that help? I mean, but then x3 will also be somewhere. That will become a y1 bar. Okay, so let me ask this question. Suppose there is no pure class. What does that mean?
Excuse me, sir?
Yeah.
Sir, if every clause contains a variable in negation, then our k becomes 0.
Then you can satisfy the entire formula by setting every variable 0.
Yes.
Yes. So if there is no pure formula, pure clause, problem becomes simple. You can set all the remaining variables to 0 without using your budget of k. You can satisfy the formula. So that's the answer, right? So what do you do? So this is not really pre-processing. This is in some sense a post-processing. So you find a pure clause, branch. When you branch in a pure clause, your k drops by 1 at least in each branch. Keep doing this as long as you reach the stage where there is no pure clause. At that point, set all the remaining variables to 0. You will satisfy all the clauses. Anything. So you will, but the point is every clause has something negated, right? So if I set all the remaining variables to 0, then every clause will be satisfied because there is some negated variable sitting there which has been set to 0, so it will set to 1, right? So branch, okay, so find as long as there is a pure, there is a clause with both literals positive, branch on it, right? So, k drops and your height is going up to k. When every clause has some negated literal, set all the variables to 0 to satisfy the formula. So, this is like a 2 power k algorithm, because whenever you branch, it is a 2 sat. If you are talking about an r sat, it will be like an r power k, right. The same argument, as long as there is a pure clause, you just branch, r way branch, and you reach a stage where every clause is negated, somebody negated, you can set them all 0 and every clause will be satisfied. Okay, good. I think we saw lots of examples of branching. You have to be careful about how we branch, what do we branch on, and pay attention to k dropping. And sometimes, or more often, we may want to do some pre-processing which helps you to get this drop. Okay, I think next time we will get to another technique. We will get to the next chapter of the book, iterated compression. So, I will stop here.